Hello, everyone. In this video, we present our paper titled Neural Scene Chronology. We propose a method for reconstructing 3D, time-varying scenes using neural scene representations. Our method takes as input a large collection of internet photos of a landmark that changes significantly over time. Here, we show example photos of 5 Z, a graffiti art center in New York City. Our output is a 4D representation of the scene. This representation allows us to produce photorealistic renderings of the scene while independently controlling the time, viewpoint, and illumination. This video shows the effect of manipulating the scene's viewpoint and time. Now let's look at our method in detail, starting with some background. All places evolve over time. If we revisit a landmark we once knew during our childhood, it might not be as we remembered it. The buildings may have weathered, or have been newly painted, or may have been replaced entirely. On the left, we show an example of such a time-varying scene, Times Square, photographed at 2 different points in time. A standard 3D reconstruction can only capture a scene at a certain moment in time. However, sometimes we might want to journey through time to see the landmark as it once was. Therefore, we need chronology reconstruction. 3D reconstruction from internet photos has been a long-standing problem in computer vision. The most similar work to ours is that of Matson and Snavely in 2014, called Scene Chronology. They used traditional multi-view stereo (MVS) methods to reconstruct a 3D point cloud from internet photos, and time-based clustering of the point cloud to enable temporal controls. However, they only reconstruct discrete planar geometry, resulting in limited photorealism. Recently, NERF in the wild and Ha-NERF used neural scene representations to achieve high-quality 3D renderings from internet photos. However, they can only handle scenes that change minimally over time, like the Trevi Fountain. When dealing with scenes that have changed significantly, like 5 Z, NERF in the wild blends textures from different times together in an unrealistic way. Now, let's see how our method works. Chronology reconstruction is challenging since each photo entangles viewpoint, content, and illumination. By content, we mean the underlying appearance of the scene, which changes over time, while illumination is related to the weather and sun position when the photo is taken. Our method needs to decouple these factors and achieve independent control over them. To decouple these 3 variables, we utilize a neural scene representation that takes these 3 variables as input. Specifically, we use a multi-layer perceptron (MLP) to represent a landmark changing over time as color and density fields. The inputs to this MLP include variables related to the viewpoint, position x and view direction d, variables related to the underlying scene content, a timestamp, and variables related to illumination, a learnable embedding assigned to each image. We can render this representation to an image using volume rendering. However, we found that fitting this model to a set of time-stamped photos using standard encodings of the input variables tends to underfit the temporal signal. Specifically, it leads to a smooth, gradual transition of scene content, resulting in ghosted appearance. As shown here, when we don't apply any special encoding to the time input, the reconstructed transition from one graffiti artwork to another occurs over several months. But in reality, these transitions often happen suddenly, not over months. NERF used positional encoding to fit high-frequency signals by making the inputs high-frequency. However, we found that positional encoding leads to severe overfitting in our case. Since both the illumination and timestamps of internet photos vary per image, if the time input is too high frequency, the model tends to assign illumination information to the time input. As shown in the video, this causes serious flickering in the reconstructed appearance. We observe that changes in the underlying content of urban scenes often happen abruptly, and this content typically remains constant for a period after these changes. Thus, we propose a step function encoding that imitates this characteristic to assist in modeling these scene changes. The step function encoding has the following form. The beta and neo are learnable and multidimensional variables. The video demonstrates their respective roles. We find that we can formulate this problem quite directly and simply, to recover a noise-free piecewise signal from a noisy piecewise signal. Here, the noise can be interpreted as the illumination, which changes stochastically, while a constant segment of the signal represents the scene content remaining unchanged for a certain period, for example, a specific billboard. Using this formulation, we explore a variety of existing encoding and activation methods, such as siren, Gaussian activations, and positional encoding. As illustrated in these plots, we find that none of them can effectively separate noise from signal in this case. However, our proposed step function encoding performs this separation successfully. When we apply this to the scene model we propose, it effectively disentangles the illumination effects from content changes in the underlying scene. Now, let's look at some results. The first video is our rendering result on 5 points. As illustrated in the video, the proposed method can render images with the controlled viewpoint, time under the fixed illumination. The proposed step function encoding allows for generating fast transitions without overfitting illumination effects. In our experiments, we showcase the capability of our method to manipulate illumination in the rendered images by selecting a suitable illumination embedding. Here, we show our ability to control the scene's lighting while keeping the viewpoint and time constant. Here, we illustrate the effectiveness of our approach on Times Square, where our model enables independent control over viewpoint and time. Here, we show our method's ability to control illumination separately from scene content on Times Square. Finally, here are the results for another scene, the Metropolitan Museum of Art. Thank you for your attention. Please visit our webpage for code, data, and more information.